Uh, Why don't we begin today's colloquium? So today's speaker is Tarique Siddiqui, and he completed his integrated Bachelor and Masters of Science degree in Exploration Geophysics from the Indian Institute of Technology in 2012. And then he was a PhD student in the Earth's magnetic field section at the GFZ in Potsdam from 2013 to 2017. And his thesis title was Long-Term Investigation of the Lunar Tide of the Equatorial Electrojet During Sudden Stratospheric Warming. And he received his PhD last fall, and then he moved here as a postdoc, I think in December or so, maybe around that time, where he has been working with Astrid on some modeling and observations. And his research interests are studying the vertical coupling in the atmosphere, atmospheric tidal effects in the MLT, and the ionosphere and ionosphere electrodynamics. And today he will present on the relationship between the lunar tide of the equatorial electrojet and sudden stratosphere warming.
Thank you, Nick, and thank you everyone for coming to do this talk. I would like to take this opportunity to thank, first of all, my supervisors and my collaborators here at HAO and back at GFZ in Potsdam and at IAP, Kulungsborn. I'll first, the outline of the talk goes as follows. I'll give a brief background about the topic, then I'll talk about the techniques we have used, followed by three main results that I'll discuss in this talk. The first and the third one was done while at GFZ. Second one was done here since October, and then at the end I'll show the conclusions. My first slide is about the STSW, and so this event was first discovered by Richard Scherhag in Berlin in 1952, and it is best explained through a set of figures. So here in the first figure, you see the air temperature at the 10 hectopascal level in the northern hemisphere, and you see a stable polar vortex. And if you look at these dates, the wind and the temperature here are, go back, the wind and the air temperature are at the usual levels, but as there's an increase in the planetary wave forcing from the troposphere, you see an instability in the polar vortex, and here you see the increasing instability in the air temperature and wind too. And then this instability increases, and ultimately you see a split in the vortex. So it can also be that the vortex just gets displaced off the pole, and you have a warming at the North Pole. So SSWs can be of two types. The first one, it can be a vortex displaced type, where the vortex just shifts off the pole. It can also be of another type, where the vortex it splits into two daughter vortices. And why is it happening? It is due to the amplification of the planetary waves. They in the troposphere, and then they go up and they deposit the momentum in the stratosphere, leading to these phenomena. The mechanism can also be explained in the next slide. So you see that due to SSW, you have two circulation cell which develops in the stratosphere and the mesosphere. So the stratosphere cell is due to the forcing of the planetary waves. So this they force in a westward direction, and due to Coriolis force, you have a deflection towards the pole, and this induces an equatorial to polar meridional circulation. But in the mesosphere, you have opposite circulation which gets ensued due to forcing of the gravity waves. So here you have eastward forcing, and the middle circulation direction is from the pole towards the equator. So what we get is we get cooling here and a warming here. So this air comes down and it adiabatically heats up, and you get warming in the polar stratosphere, cooling in the equatorial stratosphere, and in the mesosphere you have the opposite behavior, where you have cooling in the polar region and warming in the equatorial region. So the impact of the SSWs are not limited only to the polar regions. It can extend to other atmospheric regions too. My next slide shows the summary of the effects of the SSW that we know so far. So you have the SSW warming here. In the stratosphere, you have cooling in the mesosphere. Then you have also thermospheric warming at the poles, and in the equator you see the opposite behavior as I showed. And then due to SSWs, you see also the effects on the ionospheric current systems in the electrojet and the SQ current system. And this happens because due to SSW, there's a modulation of the atmospheric tides, and these tides change and then they go up and they disturb the ionospheric current systems. I also want to give a short background on the equatorial electrojet and the atmospheric lunar tide. So the electrojet is a narrow ribbon of current that flows over the deep equator in the E region of the ionosphere, and it is a very thin current flow, and it is a daytime phenomena, and it is very sensitive to the tidal behavior. And the atmospheric lunar tide is due to the forcing of the moon in the lower regions of the atmosphere, and these perturbations, as they grow up, they gain in amplitude, and they reach substantial amplitudes in the E region of the ionosphere, and they drive the electrojet current flow. They have effects on the electrojet flow. And so if we look from an observatory, from observatory on the surface, what we see is that the lunar tide shows so on a day-to-day basis we have variation in the lunar time, but if you look at one fixed time, you see a semi-monthly oscillation in the lunar in the geomagnetic tides. So the lunar tide will show a semi-monthly oscillation at a fixed local time, because one lunar day is not equal to one solar day. I mean, if it was a solar tide, you see a fixed tidal amplification for each local time, but for the lunar tide, it's different, because one day it will peak here, then the other day it will peak a bit slightly ahead in solar time. Now the enhanced lunar effects in the electrojet, this is not a very new topic. So the enhancement was first reported in a paper by Bartels and Johnston, where they reported that they find very enhanced lunar effects in the horizontal intensity of the magnetic field, and they said that that on some days the lunar effect becomes so big that they become more than the solar effects, which which is very rare because the lunar effects are 1/10 of the solar effects. And they said that it is during days of new moon or the full moon you see these effects. So here you have the moon phase 2 hours, and here you have just after the full moon. So when you have the full moon, you see that the lunar effects are increasing to a large magnitude. And they give the name to these days as the big L days, or the big lunar days. So this topic was also revisited by Onwu Meisheli in 1964, where he also found big L days in the lunar, in the electrojet in the winter time. So these observations were done in January, and Bartels and Onwu Meisheli found a number of days in these months where we saw very enhanced lunar effects in the equatorial electrojet. Now, in recent studies have shown that these enhancements happen due to the SSWs. So the SSWs change the wind and the temperature conditions, which enhances the lunar tides, and then we see their enhanced effects in the electrojet. I want to show one more slide based on the SSW effects in the ionosphere. So far we know that the effects of the SSW are not limited to the stratosphere. We see in a paper by Hanley, he showed that the SSW leads to warming in the stratosphere, then you have cooling in the mesosphere, and also thermospheric warming at the poles. And in the equatorial ionospheric region, we see that when we have the SSWs, we see a semi-diurnal perturbation pattern, something like this, which gets enhanced, and you see this pattern moves in time. So for each day, you see this pattern is shifting. And this was seen in the vertical drifts. This was also seen in the equatorial electrojet and also in the TEC measurements. So you see in the EIA, you have afternoon enhancement and evening reduction, and then this pattern moves in time with days. So some authors attributed this enhancement to solar tides, while some other authors attributed this to lunar tides. Bela Fair, he argued that these enhancements are occurring with the phase of the moon. So when we have a new moon or a full moon, these enhancements appear. And his reasoning was that this shifting pattern is more due to the phase of the moon. Now, we would like to calculate this oscillation and see if the lunar amplitudes are really enhanced during SSWs. My next section is the techniques we have used to calculate these effects. So first, I would like to tell about the sources of the magnetic field. So when we record here, when we have a magnetometer at the surface, then we are recording, we get the effects of a number of magnetic sources. The main effect comes from the main field of the Earth, which is in the outer core. Then the effects of the ring current and also the effects of other instabilities in the ionosphere. But at the equator, the major effect comes from the electrojet and the SQ current system and the Earth's internal field and the effect of the ring current. So here's an example of a recording at the Huancayo Observatory. You see the H component recording here, the horizontal component, and we will use these type of observations to calculate the lunar amplitude. So how do we do it? So the easiest way to calculate the strength of the electrojet from magnetic field recordings is to take two observatories, one which is just below the deep equator and under the electrojet, and one we take outside the electrojet region. For the one observatory located below the electrojet, you see the effects from four main sources. You have the effects of the Earth's main magnetic field, then you see the effects of the ring current, which is the magnetospheric current. You have the effect of the SQ and the effect of the electrojet. Now at the off equator station, you have the effect of the Earth's main field, the ring current and the SQ. Now what we assume is that since the ring current is located between 3 to 8 Earth radii, so that effect would almost be similar at these two observatories, which are say 500 kilometers apart. So it's a good approximation that the effect of the ring current is equal at these two observatories. And the Earth's main magnetic field can be approximated if we take the nighttime values. So then the conductivity is very low, and the main contribution comes from the Earth's main magnetic field. And to further choose a very good approximation for the Earth's main magnetic field, what we did is we chose only the 5 international quiet days value when the effect of the ring current is very low. So then we took the mean of those 5 nighttime values to approximate the Earth's main field. So we subtract first the observations of the equator from the Earth's main field. So what we are left is delta H equator and H off equator. Now if we subtract these two values, we'll effectively be removing the effect of the ring current and some part of the SQ from the electrojet observatory. So what we get delta HEJ is by subtracting these two values. So this gives us a good approximation of the electrojet value from the magnetometers on the ground. So now the next part is that how do we remove the now the main variation in the electrojet is not the lunar effect but the solar effect. You see here the daily variation of the electrojet, and here you see the peak amplitudes in the noon time and near the noon time when you have the maximum overhead sun and the highest conductivity, then you have the peak in the electrojet strength. So how do we remove the solar tidal effects from the H electrojet we have calculated? So once we remove that, we'll be able to see the lunar tidal effects more clearly. So what we first do, we choose a 59-day. We first normalize all the electrojet values to a level of 150 SFU, because for year-to-year comparison, it is important to have the electrojet values at the same solar flux levels. Otherwise, the highest solar flux ES will dominate. So we first take a 9-day window, then we calculate the mean over each local time, and once we remove this for each local time, we are obtained with the residuals. And here you can see the lunar effects much more clearly, like the semi diurnal perturbation pattern as was seen in the previous slides. Now to compute the lunar tide, the semi-monthly oscillation, what we did is we have this 59-day window. So for each local time, we calculate the fourth harmonic component, because you can see from this relation you have 4 harmonic will give you the semi-monthly oscillation, and then we sum up for each local time. So we compute for each local time from 7 to 17, and then we also normalize it with a conductivity function, so that all the local times are represented well. Otherwise, the noon times will dominate the lunar tides. Once we have this for one window, we move by 1 day and then calculate again. So this gives us the lunar tidal amplitude for one 59-day window. Yeah. Yeah. Yes. Yes. Now, to be sure as to what we have calculated is the lunar tide, I mean, we have to validate that what we are calculating is a semi-monthly oscillation. So for that, we here, as I showed, that we calculate the amplitude and the phase. So if you look at the phase variation here, we chose the 2005-2006 as STSW event, and if you look at the phase variation of the lunar tide here, and the one obtained from CHAMP 5 years of CHAMP data, then these phase values agree very well. So what we are calculating by our method is the contribution comes mostly from the lunar tide and not from any other sources. So this is sort of a validation that our amplitudes are due to the lunar tidal oscillation. Now I want to move to the results, and the first topic is the enhancements of the lunar tide in electrojet from Honkayo data. So here, as I showed, that I took 2 observatories. One is Honkayo and the other is Fukuina in Colombia. Honkayo is in Peru, and we calculated the lunar tidal amplitude between 97 and 2011, and what you see here is the yearly variation. First of all, and the lunar tide in the electrojet shows an annual variation in with a maximum in December solstice and a minimum in the summertime. So here you can see it very nicely. And when we have the warmings, like in these years, you see a big enhancement in the lunar tide from Honkayo recordings. The red lines here show the day of the polar vortex weakening, which is a definition to calculate the day of the maximum reversal of the wind. And here we see that if you look at the blue line here is the red line here, and the green line here is the peak of the lunar tides here. So you see that there's a very good agreement that when you have the SSW event, you see an amplification in the lunar tide. Now we made a scatter and you have a very low amplitude of the lunar tide enhancement when there is less, say, reversal of the wind or no reversal of the wind. If we make a scatter plot of the peak lunar tidal enhancement day and the peak wind data, so like here we take these two dates and make a scatter plot for all these years, then you see that there's a very good linear relation between the occurrence of the peak polar vortex weakening and the enhancement of the lunar tides. And so our observations from magnetometers agree very well with the radar observations from Chow et al. They looked at two radars, one in Germany and one in Norway, and they also found a linear relation between the occurrence of the lunar tide in the MLT, and Zhang and Forbes, they found a linear relation of the amplitudes from saber temperature measurements. So our observations are consistent with their findings. My next slide shows the amplitude comparison. So here, in the previous slide, we looked at the timing of the enhancement of the lunar tide. Here we look at the amplitude of the lunar tide, and we also see that it agrees very well with other studies where they also find linear relation between these observations. Now the other thing comes up, that what is the mechanism for all these for the lunar amplification, and the mechanism can be understand by a simulation result by Stenning. So what he did in their paper is that they introduced artificial SSW in the northern hemisphere, and they showed that the amplitude of the lunar tide can get increased substantially when we introduce SSW by so what they did is that they increased the temperature at the stratospheric heights in the polar region, and with that there's a substantial change in the amplitude of the lunar tide globally. They also showed that if you reduce the winds, the northern hemispheric winds, by some levels, then also you see a major amplification of the lunar tide. So the changes in the atmospheric conditions is the main reason for the amplification of the lunar tides in the ionosphere. There's another result by Forbes and Zhang, and they showed that when an SSW happens, the forcing period of the atmosphere that moves to the lunar period, and due to this resonance effect, you see the amplification of the lunar tide. So that's one more mechanism for the amplification of the lunar tide. My next topic is to show that the lunar tidal enhancements in the electrojet are dependent on the polar vortex conditions and the QBO, and on the solar flux values. Before that, I would first like to show the data availability from the Huancayo Observatory. So you have, so we had the data from 1922 to 2010 with a massive data gap, and we got these data gaps. These were available in the form of handwritten records, and they were located in Boulder, and we managed to digitize it, and now we have a full almost 100 years of recording of the Ionosphere Observatory, apart from these 5 years when there was a Peruvian civil war and the observatory was not functioning. So this large data set makes this work possible. So we have the long-term Ionosphere data set. Now what we can do is we can look at a number of years and look at the lunar enhancement in a statistical way. So what I did is I looked at all the SSWs from 58 to recent times, and I looked at separated them into two types of events: a displaced event and a split event. A displaced event, the example is that a vortex just moves off the equator, and a split event is where it splits into two daughter vortices. And the displaced events are forced due to amplification of the planetary wave number 1, and the split event are forced due to amplification of the planetary wave number 2. And we can make a statistical study and compare the enhancement between these two types of SSW events. So here we took these events and made a superposed epoch analysis. So we see that the enhancements are much larger when we have the vortex split events. And why is it so? Because if you look at the zonal mean anomalies, they are also larger than for the displaced events. So the change in the background atmosphere is larger when we have a vortex split events, and this influences the lunar tide to be much more enhanced in that case. My next result is that we take the vortex split and the displaced events and then sort them into according to their QBO phases. So if we do that, then what we find is that the vortex displaced events have a very affinity for easterly QBO phase, but for split events we do not find such affinity for any QBO phase. But what we see is that if we have an easterly QBO and you see a vortex split, the change in the atmosphere is, change in the stratospheric wind anomalies are again much larger than when you have the westerly QBO phase, and you have a high enhancement here. For vortex displaced, you find the same thing, that for the westerly QBO phase you have lower anomaly values than when you have the easterly QBO, and you have low amplitudes here. Now, this slide shows the solar signal in the stratosphere when the geopotential height is sorted in terms of QBO phase. So this is a very famous result from a paper by Karin Lebedske, and what she showed that if we have the QBO west phase, and if we sort all the geopotential height in February according to the QBO west phase, you see that when we have a higher solar flux, there are more chances of SSWs than when we have a lower solar flux. And in the easterly QBO phase, you have just the opposite relation, that for the lower solar flux values, there are more chances of SSWs than for higher solar flux. And you can see it in this figure that when we have higher solar flux values, you see their squares. Their squares shows the QBO west phase, and the circle shows the QBO east phase. So this signal is readily seen in the Arctic polar stratosphere. We wanted to see whether this signal is also seen in the lunar tide of the electrojet, because since it is being affected by the SSWs. So what we see here is that if we saw the lunar tides in the according to the QBO phases, so we take the easterly QBO phase here and the westerly QBO phase here, and we sort this based on the solar flux values. What we find is that if we choose a solar minimum value in the easterly QBO, you see a big enhancement in the lunar tides, and if we have a higher solar flux value, then you see a lower enhancement. And in the westerly QBO phase, you just have the opposite behavior, where you have a higher enhancement when you have higher solar flux, and lower enhancement when you have a lower solar flux. So this results are similar to the results seen here in the stratosphere, where you have higher lunar tide when you have higher solar flux in the QBO west phase. So this shows that the lunar tide of the electrojet is getting modulated by the solar flux and the QBO phases in the stratosphere. My next topic is how to identify historical SSWs from magnetic recordings. So I want to go back to this slide, where the recordings at HAO and NCAR was from 1922, and the first SSWs were observed in 1952. So we have 30 years of data where we could identify the SSWs from magnetic records. So how do we do that? We first compute a superposed epoch analysis of recent years and calculate the lunar enhancement, and we calculate this top base value. So this is the threshold value which can be used to locate the SSWs in the past before their direct observations, and then we look at the lunar tidal amplitudes from 1926 to 1951. And if we take this top value and this threshold level, and expecting that the enhancement were similar, you see that we can identify these historical events that were not observed before. So it is possible to identify, it could be possible to identify historical events from ground magnetic recordings. That's my results. I just like to conclude that what we find from our results is that the enhancement of the lunar tide in the electrojet are very well correlated with the data and amplitude of the polar vortex weakening, and our results are consistent with other results from MLT winds and in the Sabre temperature amplitudes. And we find that the lunar tide in the electrojet is getting modulated by the QBO, and it is possible to identify historical SSWs from magnetometer recordings. Thank you. Yes.
Up there.
Yeah.
Now that goes from 1942 to 2007, the plot on the right.
Yeah.
I would argue that if you plotted the F10.7 on a 50-day smooth curve for daily record, you'd find that those dots are not occurring at random places, right? So they're not randomly spread.
No.
These
dots?
Yeah.
No, but these are events. So these are SSW events.
They're SSW events,
yes.
But they're also solar events.
No, the SW has no connection with the
sudden stratospheric warming?
Yeah.
So why you plot them on that curve then?
No, to show that that when you have a higher solar flux, so that SSW will be most likely to occur in the west phase of the QBO.
Okay, I'm going to send you a plot later, and you'll see. We'll talk about what I'm talking about.
Okay.
The F10.7 was very, very strongly modulated inside of an 11-year solar cycle.
Yeah.
But that corresponds to other things that are going to be black in the atmosphere, especially the polar atmosphere at that time. So, anyway, I'll show you later that it could be complete crash culture still.
But I think this is just to identify the events, right?
Yeah,
Just to show that you have a distribution of events.
Yeah, but
at
there
a
could be
variety
more to
of
it.
conditions. So, this might just be semantics, but when you speak of the lunar tide, that's a gravitational tide.
Yes.
Right? And the reason that it is self-modulated, full moon, half moon, is because there's also a solar gravitational effect, which combines with the lunar gravitational effect to make a total gravitational effect. And that's what we call the lunar tide.
Yeah.
Right? At least that's the way it works in the ocean.
Yeah.
Right. So I assume that's the way it works in the atmosphere. So, so what we're calling the lunar tide is really a combination of a lunar and solar gravitational tide. It's modulated according to the lunar orbit. Right? Whereas what we're calling the solar tide is a solar heating.
Yes.
Tide.
Yes. Yeah.
Come back to the regression. Earlier you said you normalize the J by the solar flux. Later you said since the lunar tidal actually also has some relationship solar flux.
No, but those were normalized amplitudes.
Yeah, I know that. I was wondering, with the normalization procedure, not sure how this is done, but the normalization procedure, but some of the dependence of the lunar tide on the solar activity also got all synchronized.
No, but that solar flux is just to sort out the QBO and the solar flux effects, and I mean we have to normalize. Otherwise, you'll have a higher lunar amplitude when there's a higher solar flux because of the electrojet dependence of the solar flux. So what I mean, those results were for normalized amplitudes, and I was comparing them with the solar flux and the QBO response of the Arctic stratosphere. So not with the lunar tides. Yeah.
To this picture, when you remove solar tidal events, can you do vice versa, remove now lunar tidal effects and see what will be the solar effect.
But
Does it make sense?
Yeah.
So in that sense, basically the question is as follows, especially it's regarding to interpretation of amplification of lunar tides due to anomalous zonal wind circulation in the polar stratosphere in Arctic events. Did anybody also do investigation how the solar thermal tide amplified into this?
Yes.
I saw in the papers how lunar tide amplified by 9 meters per second, but I do believe, according to vacuum results, solar ional tide amplified like well. So in that sense, I just would like to make sure what the quantitative relationship between more important. Yeah.
No.
So of course we will be active during different time, but
I'm looking at them right now, but I've
this
not
will be very good
shown them.
to show relative impact, relative importance.
Yeah.
We hear now solar tide important, lunar tide important. Of course, maybe combination of both important, but it would be good also to make quantification.
Yeah. The one thing to I mean on this issue is that it varies from year to year. So for 1 year you could have a higher lunar tide and a lower solar tide, and the other year you could have amplification in both the tides. So that's an issue to deal with.
It was really interesting topic to continue.
Yeah.
Interesting how you can sort of use the ionosphere detector as perspective warnings. Back in 2002, there was the first ever observed southern hemisphere flash outflow. And I was wondering if you looked to see whether or not that was signaling, you could see that signal in the summertime in the red detector. And if so, if there are long-term records, you actually go back and see just if there were indications that there had been additional stratospheric warming in the southern hemisphere prior to the satellite record where we actually see it.
Yeah. But the issue with this, there's the issue that the lunar tide becomes so weak in the summertime that it is difficult to isolate it. And
why is that? It's because of circulation?
yes, yes, circulation because of the
circulation?
summertime conditions.
So it's not symmetric.
No.
But I thought there was some study that showed that there was some effects of the ionosphere during the 2002 for southern hemisphere.
Yeah, but I mean, the lunar tide, I don't think so. But I mean, you see some effects maybe if you have the radar in the southern hemisphere.
One of the fellow students had a paper on this for the ionosphere.
Yeah, I don't see it here.
Yeah, I think it's kind of under climatological normal conditions that if you, as you said, you circulation with the jet is so strong. But during STSW, the jet weakens and reverses, so you would think the resonance condition would be matched too. So there should be a, I would think that there should be a spike, but I don't know. Just if the force theory is true, then you would think that that should happen.
Yeah, but it also has to be at the whole atmosphere changes. It is not due to the SSW changes are seen over the whole atmosphere. Or is the summertime change also across the whole atmosphere? I mean that we
But you're
don't.
saying
Yeah.
that even if the whole atmosphere changes, the ionosphere signal might be weak because the ionosphere is weak during northern hemisphere, what we call summer.
Summer, yeah.
We find the ionosphere to be weak during June, July for a variety of reasons which are still in dispute, but it's an observational fact that there's less ionosphere on the whole than in July. Well, I don't know. That part I've never really thought about. I know that climatologically, there's this big hemispheric symmetry between the solstices. think that's what you're referring to when you say that
Ionosphere is weaker.
nitrogen is also weak just because there's less ionosphere to push around. Although the E region, this is the F region ionosphere.
The E region too, I mean,
It's, of course, much more symmetric.
And what would be the best vertical level height to make indicators of this wave analysis for electrojet index? For instance, type 100 kilometers, 90 kilometers, 110, 180.
I think the mesospheric heights would be the
Which one?
mesospheric heights.